What is up, most distinguished patrons of this channel? Today I got a special for you. On today's episode of Shit I Shouldn't Be Buying, I picked up this old Lincoln Tombstone so we can sort of disassemble it, test it, get an idea of how it works and how old school welders produce AC and DC output, and learn a little bit about electricity in a safe manner where none of us get shocked. So with that said, let's get into it. So this welder is so big it doesn't even fit in a frame, and I apologize. But anyways, I picked this sucker up off a Facebook Marketplace, got a pretty good deal on it, paid around 200 bucks, which might sound like a lot. However, this is not just the AC only version. This one is capable of DC output. The DC output ones are fairly rare in comparison to the AC tombstones, and in my opinion are more useful because DC welding in general is how everyone stick welds even to this day. AC only limits rod choices among other things, and I'm not a big fan of AC sticks. So from a usability standpoint, this is still somewhat relevant in today's world as far as welding with it. Now, one of the interesting things about tombstones like this is that, well, a lot of us got our first taste of welding on a machine identical or very similar to this. So this is very relevant to my childhood when I was learning to stick weld, aka I just stuck rods and didn't do anything, got frustrated and gave up. But this is the very first welder I had any experience with. My father bought one, he welded up stuff with it, and then I, like I said, struggled, couldn't really do much with it, gave up on welding for a very long time, and then came back to it later in life. I'm sure that you probably have also had experience with this very machine or something very similar. So anyways, what we're going to be doing today is we're going to look at every aspect of how this welder works, so aka how it converts AC wall outlet power into AC output for welding, and then we're also going to look at how it converts AC wall power into DC output. And we're going to come to an understanding of how all the components work. And this is a great machine to do that on because it is so simple. It is basically as simple as you could possibly get for a welder. And this type of technology was basically everything from the 30s all the way up to even modern day to a certain extent, still uses a lot of the same concepts and design thoughts as this machine does. It's just that technology has brought us higher efficiency, aka this machine weighs probably 50 pounds, heavier than hell, has very large copper wound transformer in it, and the components on here are very expensive to make, very heavy, and very inefficient. And speaking of that, we're even going to test the efficiency of this as well. But what I'm getting at is the principles that we will find in here are very similar to modern machines. It's just thanks to technology, modern machines are smaller and more efficient. So to start things off, we're going to do a little bit of book learning to understand how this machine works, and then we're going to look at the actual components that do the job that we're going to see in a book learning, and then we're going to actually look at different aspects on an oscilloscope to see exactly what's going on. So the first thing we need to cover is a very simple principle of transformers, because that's what this machine uses. It's known as a transformer machine, but truth be told, all welders have transformers in them. It's just the modern ones are far more efficient for a lot of reasons. But all the transformer in this welder does is it creates usable voltage. So this machine is 240 volts only since it's designed for North America. These were shipped all over the world likely, and the voltage they operate on would be unique to your country's electrical grid. But here in North America, 240 volts. 240 volts comes in to the machine into its transformer. Well, that's not very useful for welding. Welding with stick rods operates between 20 and 35 volts. Having that high of voltage on your stinger when you go to strike an arc is relatively dangerous, because you could become part of the circuit very easily because the voltage is high enough to overcome the resistance of your skin and your body. We don't want to weld with that. The other issue is 240 volt 50 amp circuit, because this operates on a 50 amp breaker. That's not very much amperage, and the voltage is too high. So by utilizing a transformer, we're able to convert that 240 volt 50 amp circuit into more usable 20 to 35 volt output at much higher amperage. In the case of this machine, its max output is around 225 amps. That's far more usable from, say, 30 to 150 amps or so for welding output at 35 volts than anything on the input. And more or less, that's all this device really does, is it converts unusable, unsafe power that's in your wall to something that functions for welding. Now, as far as how this gets usable output from unusable input power, it uses what's known as a transformer. And depicted here is a very simple transformer that's not too much different than what this machine actually has. A transformer in a nutshell gives you the ability to drop voltage and increase amperage. So for 240 volts, we can drop it to, say, 120 volt output, and instead of 50 amp input, we could get 100 amp output. Now, that's a simplistic look at it because there are losses within this system, but for every reduction in half on the voltage that we make using the transformer, we can double our amperage. Now, how a transformer achieves that is what's called a winding ratio. More or less, your input power goes into a spiral of wire around what's called a core. That spiral, say you have 10 or 20 turns on the input power side, the output is determined by how many wraps of wire that you have on it. So if you have 10 wraps on the input side and 5 wraps on the output side, you can effectively step down the voltage and increase the amperage potential on the output. Likewise, if you have more wraps or more turns of wire on the output side of the transformer than input, you can increase the voltage at the expense of amperage. So again, say we had 10 wraps of wire on the input and 100 on the output, we could significantly increase this voltage. But again, welding operates at high amperage, low voltage, so every welder with a transformer, which is basically every welder, has a lower number of turns on the output than the input. And that is what gives us usable welding current. To help understand a little bit more about what's going on here, we need to understand something called wattage. And wattage is basically a number that's given that references the actual electrical power that we're dealing with. Now, in the case of this machine, 240 volt, 50 amp circuit, if we were to max that circuit out, aka the machine is set to max, we would likely draw or load the input lines somewhere to 12,000 watts. And again, all it is amps times voltage equals wattage. Now that is on the input side. On the output side, this machine is rated at 25 volts output at 225 amps. That is approximately 5,625 watts. Now, you're probably asking yourself, if the input is this much power, how on earth could the output be so much less? And here is the reality. Anytime you convert, say, a high voltage to a low voltage or a low voltage to high voltage, there are losses in the system. In a perfect world, 12,000 input wattage would be 12,000 output. But everything has losses. In the case of this old machine, the transformer itself is fairly inefficient. So the conversion process that is happening here is very inefficient. It also has what's called very poor power factor. That plays a role in it as well. And a lot of that energy that is lost in the form of heat. Therefore, that is why this has to have a big giant transformer and a lot of wire to help dissipate that heat, a lot of copper, a lot of mass, because it's going to get hot. Now, this is what it's rated at. Realistically, it's probably going to output somewhere, I would say, more wattage than what you see here, because it likely will be able to output higher than 25 volts at its max output. In reality, and we're going to actually test it in this video, this machine is probably somewhere around 60% efficient at taking input wattage and converting it into output wattage. which in reality means that 40, maybe 50% of all the electrical energy this device consumes is wasted in the form of heat. So that is pretty atrocious. A modern machine, modern welder, typically are somewhere between 85 and 92% efficient, which is why all modern machines can get by on a lot less than a 50 amp breaker and can often weld on 120 volt low voltage and get decent outputs, whereas this machine simply can't, and that is due to its inefficiency. Now, hopefully all of this makes sense. Let's talk a little bit about how this device actually controls the output amperage. So this little chart here should help us understand a little bit more of what's actually going on with this transformer. We have 240 volt, 50 amp circuit, 60 hertz is the frequency. This is in North America. And we have 10 turns or 10 wraps of wire on the input side of the transformer. On the output side, we have 5 turns or wraps of wire, and that effectively gives us a 10:5 ratio, which is going to reduce the voltage and give us more amperage. So we can more or less convert 240 volt 50 amp to 120 volt, half the voltage, at double the amperage. Now this is in a perfect world. As I mentioned before, these things are not perfectly efficient, nowhere near it. So our actual output and voltage is going to be less because of basically heat and other system losses in this. So in a perfect world, this is the conversion. Now, 120 volt at 100 amps is really still too high a voltage to be useful for welding and still borderline dangerous, likely to shock you. And 100 amps is kind of limited, so we need more amperage. Well, by effectively putting on the input side 20 turns of wire and 5 turns on the output, that would give us 60 volts at 200 amps. So again, by doubling the ratio, we can half the voltage output and double the amperage. Now this is pretty close to what this machine outputs. So we're getting in the ballpark of what would work well for welding. So that's a good thing. Now, as you notice, again, this is still 12,000 watts. In the real world, you will never achieve 100% efficiency through a transformer, especially at lower frequency of input power. So this is closer to like 6,000 or 7,000 watts of output, and we would not achieve these numbers. A realistic number on a 20 turn to 5 turn would probably be closer to something like 40, 50 volts under load at most, and probably 140 amps, somewhere in that ballpark. So the efficiency brings everything down. Now, to make it even more higher amperage and lower voltage, if we went 40 wraps of wire on the input and 5 on the output, we could get to 30 volts and 400 amps. Again, same 12,000 watts, but again, efficiency, we would be well under that. So realistically, inside of this machine, to achieve maximum output of its transformer is probably somewhere similar to a ratio like what you see here in order to achieve this. Because again, we would never achieve 400 amps, in this case probably closer to 250. Now the problem with the simplistic winding ratio that I have here is it doesn't give much ability to adjust amperage. And let me explain. So now in this simplistic transformer, our winding ratio is fixed, and because of that, this more or less, once you plugged it in a wall, you would only have one output level. And in the case of what we're seeing here in the perfect world with no losses, you would have 120 volt, 100 amp. That's not very usable for welding because welding takes place at multiple current levels with stick welding. Therefore, we need to have some adjustability. And how this machine adjusts amperage output is really simple. All it does is it takes advantage of variable winding ratios. As we discussed, a change in the winding ratio will change the amperage that you can pull through that transformer or that you can weld with. Now, you're probably asking yourself, well, since this is just wire wrapped around a core, how effectively can you change the winding ratio without rewinding the wire? And the answer is simpler than you're probably thinking. What this machine does is it simply taps off of a different point on the coil of wires depending on what setting you have the switch on. So right now it's 10 to 5 if you go between this wire and this wire. However, if you were to go between this and this part of that coil of wire, you effectively would have 1, 2, 3, 4. You would cut off at least one turn, and you would change the ratio of the input versus output. Therefore, you would change the amperage output capability of the machine. And you got to remember, we're talking about stick welding here, and stick welding works on what's called CC, or constant current variable voltage. We're interested more or less in regulating how much amperage can be pulled through or output out of the machine, and we don't really care about regulating voltage as much. Therefore, by manipulating the winding ratio, we can get into usable current ranges for particular stick rods simply by tapping off a different point on the coil, and depending on what wires you go through gives you different maximum current. So that switch on the front of these tombstones, all it's doing is basically tapping off different parts of the coil. Now, this is a very simplistic design with very few turns. The transformer in this machine would likely have a lot more turns, say 150, 200, or whatever on the input, and the output would be far more turns, and by having more turns, it gives you more points that you can tap off. Like say this had 25, well, you could technically split any point of that between the start of it, and you could get 25 different potential outputs. And that is why this machine has 40, 60, 75 amp, 90, 105, etc. For outputs, it's just tapping off the output coil at different points. So this is probably one of the more simple designs for regulating amperage just by exploiting a transformer. Now, predating these machines with a switch, they often had different ports on the machine where it had, like, where you could plug in the output lead in any one of them. And I'll put up some pictures of these machines now. All of those machines function identically the same to this Tombstone. The only difference is, rather than having an internal switch that picks which wires off the coil that you're going to be running off of, you're manually hooking to that. So it just doesn't have a switch, but it still functions the same. Those would all predate the design of this Tombstone. This would have been considered like newer technology, having the very simple switch on it. So that's how this machine and all the machines similar to it regulate amperage, but it's not the only way that a lot of these old school transformer machines work. All right, let's talk about how this machine generates DC output. So on an AC only Tombstone machine, you would more or less just have your transformer and your selector switch that changes the winding ratio, and that's it. You weld with it. There are virtually no other components inside of the machine. It's as simple as you can get. Well, on this particular one, it has DC output, and this applies to any DC output capable transformer welder. They have a couple more components to give you the capability of having DC power, because DC tends to run certain rods better. Some of them really need it to run, so it's important to have DC capability, in my opinion. Well, most of the older school machines create DC using what's called a bridge rectifier, and that is depicted here. In simple terms, all a bridge rectifier is a series of one-way valves that will allow electrical flow in one direction and not the other. And you can use that to your advantage to basically create a pretty poor version of DC output. AC output, which is depicted here, you have voltage plus and minus off of 0 volts. That's what's coming out of your transformer. All a bridge rectifier does is it flips the bottom part of the waveform to where it looks more or less like this. So this would be your 0 volt line, and it's flipping this up to here. And that gives you only positive voltage output. So that is technically DC because it's only staying on the positive side per se. But the problem is, if you look at this waveform, it's coming up to whatever the peak voltage is, dropping down to 0, up and down. When that waveform hits 0, it can be difficult for a rod or an arc to stay lit, to stay functional. And what will happen with a lot of rods with this type of output out of this bridge rectifier is they'll only stay lit for a second or two and then cut out, which is why if you have one of these machines and it won't weld on DC, but it welds on AC, more than likely these diodes, these one-way diodes of the bridge rectifier are bad, and simply replacing them will give you the capability to run on DC. That is also why the AC waveform typically does not run a lot of rods well, because they can't stabilize, the machine doesn't stabilize the arc very well. Certain rods, like AC versions of them, work good because they're designed to help keep that arc lit as it crosses 0 volts. So again, you know, on this is very poor to stick weld with, and that is why this machine and virtually all other DC rectified transformers have a form of a choke, or what's called in the industry, they call it a welding reactor typically. And what that is a big coil of wire that looks like a transformer that they put on the output of the bridge rectifier, and it functions as a choke, or more or less the peak voltage. It tends to resist changes in voltage. So as the voltage comes up, that big mass of copper is resisting it. So it kind of comes up like this. So the peak voltage is less, it's pumping the brakes on the voltage rise, and then as it drops off, it's kind of stepping on the gas in a way. It's resisting the change of voltage. So more or less, that reactor, or that choke, is creating a smoother ripple. So it doesn't hit 0 volts where the arc cuts out, and it doesn't hit a high peak voltage. It normalizes it. And this gives a much cleaner output and makes it a lot easier to run a lot of rods, because again, you're not hitting that 0 voltage. Now, the biggest thing that you kind of really need to understand about all of this is this machine, and basically all older transformer machines, really operate on very simple, well understood electrical principles. And because of that, and how simple they are, they tend to be very reliable, because what goes wrong with these machines really is, okay, if the wire here gets nicked somehow and shorts out to the core, well, that would be a problem, but the coating on the wires typically lasts in decent environment 70, 80 years without, you know, major issues. The main component of this machine that would fail would be the diodes of the bridge rectifier, but those are individually replaceable, and it's very easy to test them. So you just need to verify that continuity in one direction. If continuity exists in both directions, you're screwed and you replace the component. But the overall design of this is very simple and very reliable for a very long time. But with that said, I think we're ready to look at the internal guts of this thing and find out how many spiders went to die in it. If you have an AC only version of this machine, all of these components up here, and I believe the fan, would not be included, and more or less you would have an exposed back of the switch that's on the front panel that's behind here, and you would have the transformer. But all of these components wouldn't be needed because you have an AC only machine. So these are only for the DC output capability. So let's start by looking at this transformer. The reason this machine weighs so much is solely based on this transformer. This transformer's core is a big, massive hunk of steel or iron, something that's magnetic permeable, and it just weighs a ton. Modern machines like inverter machines can get the same level of output as this by using a more efficient design. And what I mean by that is this transformer sees your 60 hertz frequency out of your wall. That's your AC frequency, how many times per second it switches positive, negative. Well, because 60 hertz on something like this is very inefficient, the transformer needs to be a lot bigger. A modern machine can basically increase that frequency to 10, 20, 30,000 times per second, the cycle rate is, and that allows you to make a far more efficient transformer to where you can cut 90% of the size and weight and still achieve the same output. Again, this predates that kind of a design or that capability, so you're limited to what's coming out of your wall. Therefore, to get the outputs that you would like, you need a big, massive transformer. Looking at it here, this here is the output of the transformer. So the secondary, this is the primary winding down here by the look of it. And more or less, the higher voltage 240 volt 50 amp circuit is hooked to this winding here, and then this is your output. This also appears to have a secondary set of windings, so it has two secondaries on it, which is likely a way that it's able to get multiple outputs. So you more or less have a winding ratio between here and here of one predetermined set. Okay, and then you have a secondary set that you can also use to vary your outputs. So that's a little bit different than what I described, but it functions very much the same. It allows you to get higher output as well as still have some lower output. And these wires here, which you maybe can't see that well, those are where that selector switch will determine how many wraps of this wire here is actually used, how many turns. And by the look of it, the secondary is a 20 turn. The primary, I can't really tell, but it's got a lot. Maybe it has 60, 80, I'm not really sure. But this functions just like I said earlier in the video. Now, interesting to note, this unit does have a fan up here, and I don't believe that the normal AC only ones have a fan, and this fan is likely to cool the components up here, so let's take a look at those. Over here, these aluminum components are heat sinks, and it's a little difficult to see in here, but these are the one-way diodes. There's 4 of them that are the bridge rectifier. So this whole component is basically the diodes and heat sinks of the bridge rectifier. This is what converts that AC coming out of the transformer down here into DC output. This right here, which at first glance might appear to be a transformer of some sort, is not. This is what they would call a welding reactor, or more or less a choke. And this is what takes the DC output of this bridge rectifier and cleans it up. So this resists changes in voltage, both up and down, and smooths out what would be the DC ripple that this creates, and creates a flatter, more stable DC output. This, in comparison to a lot of the bigger, more industrial units, is very small, especially these diodes in here. And that would be the primary reason why on DC output with this machine, you have more limited outputs. Like, you can't get 225 amps out of this machine on DC, and that is because these little diodes here would likely fail at any more than maybe 150 amps, and this would likely not be able to clean up that kind of output on DC, so this is more limited on DC output. When you look at the Dial-Arc 250s, those have massively bigger diodes in there for the bridge rectifier and a massively bigger choke on the output, so they're capable of hitting well over 200 amps on DC output without any issue. And it's just bigger, more industrial components, which this didn't need because of the target audience. Now, I'm not going to take this panel off any further because there's really no need. It's just that switch, the switching components, the manual switches for all of this to determine whether you're going to run on AC or DC. And all of those really do, the AC-DC switch is just whether or not this componentry is included in the circuit. If you're on AC, only the transformer is used. If you switch it to DC, then all of this becomes electrically live and functional. So now is going to be the fun part, where I'm going to power this thing up and hook an oscilloscope to it so that we can see how this functions. Up first is a screen capture of the oscilloscope. What we're looking at is the input and output of the transformer, so basically the primary and secondary sides of the transformer. Now, don't pay any attention to the numbers down below. That's all inaccurate. I captured the waveform and kind of edited this to make it work, but don't pay any attention to that. The blue line represents the alternating current input, which is around 250 volts or very close to that. And then the orange line represents the output to the transformer. Keep in mind there's no load on this transformer right now, so the waveform isn't distorting at all. But that transformer is essentially dropping the voltage to something that's far more usable, which is around 70 volts. Now, if you recall, we don't weld with stick welding at 70 volts. That is just the resting voltage. Once you strike an arc with it, the voltage is going to drop to whatever it's required to maintain the arc. So in the case of most rods, somewhere between 25 and 30 volts. In case you're wondering, this type of a transformer and welder setup will only work for stick and TIG, which are constant current variable voltage. This would not work for wire processes, which require constant voltage variable amperage. Well, now let's take a look at how that reactor / choke works to smooth out the DC ripple. Let's focus on the oscilloscope on the left there. What you're looking at is the input and the output of that welding reactor that is used to smooth out the bridge rectifier. Now you can't really tell too well, and I apologize for it, but the waveform you're looking at is actually what's after the bridge rectifier. So more or less this less than perfect waveform is the AC that went into the bridge rectifier. This is converted to DC, so all of the spike that you see there, all of the voltage is actually above 0 volts. So it's not going and alternating positive negative per se. This is all DC, and that's why it lists the cycle rate on there as being 120 hertz instead of 60. That's because, well, it is cycling 120 times per second, but it's all more or less DC. Now, if you were to try and weld with this straight out of the bridge rectifier, what would end up happening is a lot of rods wouldn't stay lit, and you would have more or less a pulsing current 60 times a second. You would have a lot of issues with the rods running properly. So that is why that reactor or choke is put on after the bridge rectifier, because it's going to take and completely clean that dirty, waveform of DC and make it more or less a straight line consistent voltage. And we'll look at that in real time now. So the orange-red line is the input to that choke, and the blue line is the output. And once I strike an arc, you're going to notice how it more or less changes to straight DC that's very clean. So let's watch that in real time. So as you saw, that DC output is very stable, very clean, and it's honestly probably better than a lot of the more modern inverter machines that are out there, especially the cheaper stick welders. And that's why people give these old machines crap as being power hungry, which they are, and heavy, which they are, but you can't argue that their output isn't smooth, and it's very clean DC, and they weld great. All right, let's move on. So the moment of truth, the moment all of you guys have been waiting for, and that is exactly how efficient or, inefficient is this bastard. And I ran all of the numbers and came up with some answers, and it's not too surprising. So first off, at 45 amps DC, so with it in DC mode, it consumed 1,600 actual watts, and that is corrected for the power factor, and the output was 920 watts. So that would put it at about 56% efficient, which is absolutely abysmal, but not really too unexpected. Any of these older transformer machines, if you can hit above 50% at taking input power and converting it to output, you're doing pretty good. In case you're wondering what happened to the other 44%, well, in this transformer here, I would say a vast majority of it went because this sucker's still warm and it's been off for a good hour and unplugged. Not to mention the bridge rectifier and that choke reactor that it has up here also are very warm, and I barely did any welding. I ran a couple of rods with it and it's still warm. So this thing is more or less basically a space heater. So somewhere in the neighborhood of, I would say, 400-500 watts is just being produced as heat. So it'll keep your shop warm if you got decent insulation. Now on AC, 75 amps, a little bit higher of a setting, it was 67% efficient. And that's with taking the input output and calculating that out. And you're probably wondering, well, why is it more efficient on AC? And the answer is very simple: because we removed the bridge rectifier, we removed the big giant choke, and all of that stuff which does consume and produce heat. With that out of the circuit entirely, we have better efficiency. And I gotta be honest, 67% calculated efficiency is not that bad, and not as bad as I would have suspected it would be. So, you know, that's really not that bad, honestly. Now, what is absolutely atrocious with this is the power factor. It's probably got the worst power factor I've ever seen of a welder, as to be expected with the way that it works. And the power factor is a major concern for two reasons. One, to actually get this thing to weld above 100 amps, you're definitely going to need a 50 amp circuit. To put it in perspective, when I was welding at 75 amps on AC, the actual input line saw a loading of 31 amps. It almost tripped the breaker. It was right about to trip the breaker on the generator I was running this on. So that, unfortunately, if you have a 30 amp breaker in your house, to get, I don't know, 100, 120 amps, you're probably at 120, you're going to end up tripping a 30 amp breaker. So you really need a 50 amp breaker. Now, if you're a person like me and runs your equipment on a generator due to where you're at, guess what? You're going to need a 13,000 watt generator, aka one with a 50 amp breaker on it, in order to keep this thing from tripping the breaker. And that's why when guys ask me, what welder should you run on a generator? Don't run one of these on a generator. The poor power factor is going to be an absolute nightmare to deal with. You're going to have to deal with trip breakers. You're going to have to deal with the waveform coming out of the generator, the AC waveform deteriorating because the power factor, the reactive power is so bad. Long story short, you should never run one of these on a generator if you care about the generator. This thing doesn't matter. It doesn't care about the quality of power going into it for the most part, but the generator will get smoked running this on it more than likely. Also of interesting note, at idle, it consumes, and this is actual consumption, 320 watts just sitting idle. So that is quite a lot of power for just sitting around doing nothing. And by the way, that was without the fan running in there. I had the fan disconnected. So just residual power consumption, that's pretty bad. And again, it's all going into heat. I mean, this thing I welded for a grand total of about maybe 5 minutes in the hour that this thing was powered on. And I'm not joking, like this transformer, it's still warm now, but it was warm just at idle. And that's one of the big reasons why modern welders really got away from this whole design, is it's just so inefficient and wasteful. It just isn't really cut out for the modern electrical grid per se, aka you can get similar outputs to what this has at 225 amps easily on less than a 30 amp circuit in a machine that's a quarter of the size of this. So pretty crazy. Well, let's go to conclusion. So in conclusion, what did we learn today? Well, hopefully you learned a little bit more about how these old transformer welders work, and you learned a little bit about the efficiencies or lack thereof, and you learned a little bit more about how even though these things are old, they still work, they still weld decent. And if you want to invest in something like this, because they're cheap. Like I picked this up for 200 bucks. $200, it's hard to go wrong with that. I mean, this thing will last 5, 10, 15, 20 more years, no problem. So that's not a bad investment. However, if you have any ambitions on running on a generator or you have limited power, you can forget about running one of these. And that's why, in my opinion, I'm a bigger fan of the modern inverters, and I know some of you out there might be boo-hooing me about that, but the truth is that I can get similar output to this in a package that's the size of a shoebox or smaller, that's actually portable. It's not going to trip a 30 amp breaker, and for the most part, they weld better or equally as good as this. And one thing I can't really put into a video and explain is that the weld quality when you're welding with this on DC output is actually not bad, and it welds really good. I have no complaints about that. On AC, which I'm not a big fan of stick welding on AC, personally I don't really like it. I wouldn't buy one of these that's AC only. Honestly, don't buy one. Get one, if you're going to buy one of these, get one with DC output. It just runs a lot of rods better. It's just all around a better welder. But again, if you're looking at buying something for around that $200 price range, my honest opinion is go down to your local Harbor Freight with a coupon and get one of them titanium 225s. That's actually an excellent stick welder. It runs 60-10 perfect. And even though it's very simple, it will do everything that you want in a affordable, small, portable package that's far more efficient than this. So it's just something to think of. But anyways, this video was fun to make, and honestly, it kind of reminds me of how far I've come as an individual, because the last time I actually welded with one of these, I basically just stuck a bunch of rods with the one my father had and then gave up stick welding, and here I am, I don't know, 30 some years later, picking it up, this time disassembling it and being able to weld with it. And it's just, I don't know, nostalgia is a real thing, and I'm getting old enough to where it kind of matters. It hits me right in the feels, I guess. Anyways, hopefully you enjoyed the video. If you got any comments, questions, thoughts, you know where to leave them. Until next time.